Guys, we only have 2 more chapters left. Chapter 22, which is definitely one of my favorite chapters, full of some of my favorite reactions. So I'm really sad that we are not going to be doing this one together in person. 22 is on alpha carbon chemistry. So let's talk about what is an alpha carbon. So the notation alpha carbon is specific to compounds that have carbonyl groups, like a ketone, like we've drawn here. Instead of numbering the carbon chain like you would number it in IUPAC, so here's how we would IUPAC number that carbon chain. An alternate way of numbering the carbon chain is to use the Greek letters starting not at the carbonyl carbon, but adjacent to the carbonyl carbon, and then counting out like that. So alpha, beta, gamma. And one of the problems with this system is that there are 2 alphas, or there could be 2 alphas. So this is like an old school pre-IUPAC common notation that still hangs around for some biochemical stuff, but we don't see it that often in organic chemistry. So we are focusing in this chapter, we're focusing on the chemistry that is taking place at these alpha carbon sites. And they do some interesting chemistry. So the first thing that we have to talk about, which we just did, is what's an alpha carbon, and then also the hydrogens that are bonded to alpha carbons. Those are called alpha hydrogen because they are on the alpha carbon. So the reactions that we're going to study in chapter 22 have to do with doing like substitutions at the alpha site, deprotonation at the alpha site, things like that. And on this first section, this first worksheet, we're just kind of looking generically at the reactivity of these alpha hydrogen and alpha carbons. So here, and this shows a really common reaction that can occur at the alpha site. Alpha hydrogens are really easy to remove and substitute, like I had said. And there's 2 different ways that this reaction, this removal and substitution could take place. Starting here in the middle with the aldehyde, we could go, as I've drawn to the right, and form an enol. And you have seen enols before, the alkene/alcohol enol. Tautomerization in between an aldehyde and an enol, true also for a ketone. The other option, which we haven't seen before, as I'm drawing here to the left, this would be a deprotonation, forming an anion, and we call this guy the enol 8. It's a deprotonated enol, so it's called an enolate. That's where it gets its name. So these reactions that we're going to look at in chapter 22, they typically are going to start with an aldehyde, and then in one of the first steps of the reaction, we're either going to turn that aldehyde into an enol, or we're going to turn the aldehyde into an enolate and then go from there. So what we're going to do on this worksheet is look at how does that type of conversion take place. We can convert our aldehydes or ketones to an enol by either an acid or a base. So this could be an acid catalyzed or base catalyzed reaction. The first reaction that you're looking at right here, this is an acid catalyzed conversion, or it's being done in acidic conditions. I have drawn the reaction as having forward arrows. However, this is actually an equilibrium reaction that really does not want to happen. So it's strongly favoring the ketone or the aldehyde, and we have to do things with Le Chatelier's principle to encourage the reaction to take place. And so let's just fill in the curved arrows for this mechanism. Always, every single time you have an acid in the presence of an oxygen, like on a ketone, the very first thing that you should always do is use the acid to protonate the oxygen. And so that gives us this first structure that we see right here. And that structure that we can see there has a resonance structure. There is there's 2 lone pairs of electrons on that oxygen. There's 1 lone pair of electrons on this oxygen. We can move electrons from the carbon-oxygen double bond up onto the oxygen. So now it has a lone pair, 2 lone pairs, but then that does put a positive charge down on the carbon. So there's our resonance structures. And then the last thing that's going to happen is we need to do some sort of elimination from an alpha carbon using water as the base for that elimination. And that's going to give us the enol. I think that last curved arrow that I drew was kind of difficult to see. Maybe that's better. Maybe not. So that's one mechanism for the formation of the enol. We could also have this reaction taking place using a base instead of an acid. And so this time we're actually just going to come up with the mechanism ourselves. Now, this is not nucleophilic substitution. If we were doing nucleophilic substitution, like you're used to seeing, what you're used to seeing is the hydroxide or whatever going here. And it is true, I haven't lied to you, the hydroxide does still want to attack the carbonyl carbon of a ketone or whatever. But that's not the type of reaction that we're looking at right now. There are other things that that hydroxide could do. It doesn't have to go only to the carbonyl carbon. Another option for the hydroxide is to attack one of the alpha hydrogens, which would cause, the first structure that we're going to draw, cause the carbon-hydrogen bonding electrons to move down onto that carbon atom, putting a full negative charge on that carbon atom. Those electrons, that lone pair of electrons, can move in to make a carbon-carbon double bond as long as we move the carbon-oxygen double bond up to give us this structure. And the last thing that we would need to do here is just protonate the oxygen. Like that. So there's another enol. And again, this is not, don't think of this as, oh, the reactions I learned in chapter 21 are no good anymore. They are still valid. Like I said, there's just more than one option for a hydroxide or a strong base in the presence of a carbonyl. So so this is the formation of an enol with either acid or base. And that is what we've looked at there, is how we would do this reaction, starting with an aldehyde or ketone if we wanted to make an enol. We can also convert carbonyl compounds to enolates. So the enolate, that would be doing this reaction right here if we wanted an enolate instead of an enol. If we want to do this, we can only do this under basic conditions, and it needs to be a very strong base. And the bases that we typically use for this reaction are hydride, H-, and then a base called LDA, which stands for lithium diisopropyl amide. And it's a nitrogen with 2 isopropyl groups on it and a full negative charge with a lithium counter ion. So this is really, really basic. LDA is an extremely strong base. So let's take a look at how we would get the formation of enolate. We're going to use hydride. We're going to use this guy right here. And again, in chapter 21, you did learn hydride ion. It's going to want to go right here and do that sort of reaction. And that is still true. Another thing that the hydride ion can do is attack an alpha carbon, deprotonate at the alpha position, move a lone pair of electrons onto the carbon atom, full negative charge. That has a resonance structure. the lone pair of electrons move in to make a carbon-carbon double bond. The carbon-oxygen double bond moves up to a single bond. Now we have a full negative charge on the oxygen instead. And so this, what we've drawn right here, is the enolate. And again, let's scroll back up. What we're looking at is how we would do aldehyde to enolate conversion, only with a strong base. So these are the two structures in resonance. Of these two structures that we drew, which is the one that is the most reactive, which also means least stable? We're going to use ARIO to help us. Don't never forget ARIO. A stands for which atom has the negative charge. Here we have a carbon with a negative charge. Here we have an oxygen with a negative charge. Of those two, carbon versus oxygen, which one is better equipped to have a negative charge? Oxygen is much happier having the negative charge, which means that it is more stable, which means that it is less reactive. Which means that this structure right here, I'm going to get rid of the C-, this is the most reactive structure, the most reactive version of the enolate. And when we're drawing the structure of an enolate, this structure right here is typically the one that we draw. When the enolate undergoes chemical reaction, it's usually undergoing reaction in this particular form. So this is usually the way that we draw it. The enolate with the negative charge on the oxygen is not usually drawn because it's not particularly useful when we're trying to understand and explain the reactivity.